All right.
Luca, can I assume that you are taking care of the recording?
Yes. Yes, no problem.
I don't need to do anything about the
For that.
recording. Okay. Welcome, everyone. So it's exactly like most lectures. Everybody sits at the back and nobody sits in the front row. It seems like you don't learn. You can that's ingrained in human psychology, and it can't be changed. Welcome, and as you know, we are trying to go back to having seminars in presence this semester, and we have had two so far. And this is the third and last for this semester. So it's a real pleasure for me to welcome Heiko Hecht, Professor Hecht from the University of Mainz. So Heiko, I've known Heiko since we both were graduate students in America. He worked in the States for longer than myself. He worked at NASA Ames and MIT. Eventually, he came back to Germany, and he has been at the University of Mainz for now
20 years.
20 years, yeah. Okay. He has worked on many aspects of visual perception, including naive physics, and some more applied aspects of human factors as well. And today's lecture is on something where actually we studying perception can perhaps do something quite useful, because motion sickness is a real problem in many contexts. So this talk we will learn more about visually induced motion sickness today. So thank you very much.
Yeah, thanks, Marco. It's great to be here. Luca, I think my onboard microphone is on. Is the sound quality okay? Then I'll just not change.
Yes, the sound quality is okay.
I won't change anything. So what I would like to do today is just talk a bunch of studies that we've done on visually induced motion sickness, or VIMS, which is a header for a specific case of motion sickness that arises because of a conflict between visual and vestibular information. There's also other types of motion sickness, like travel sickness and space sickness and cyber sickness, that I think have the basic same underlying mechanism. So they're, in terms of symptoms, they're very similar. Okay, so what will I do? I will try to impress on you why cyber sickness is something we should really worry about, be it in autonomous driving situations, be it in cyber goggles that we use when we want to buy a new kitchen and try to figure out different arrangements of the dishwasher and the table and so on. And the motion sickness that results is a practical problem. Roughly 10% of the population, I would say, gets severely sick. The rest of us can stomach quite a bit until we get sick. But I have a recipe to make everybody motion sick pretty soon, pretty quickly. I'll go into theories, into problems of measuring it, and then I'll go into some countermeasures. So what I've been doing is trying to understand why we get sick on a theoretical level, as well as finding measures to prevent sickness or adapt people to not getting sick in particular cases. So what are the symptoms? One is general nausea, you get sick to the stomach. Another one is dizziness and disorientation, often related to ocular motor difficulties, tracking things. And there's, depending on where you get sick and how you get sick, there's different attributes that subjects may mention. But basically, it's all the same. people without an inner ear don't get motion sick. And there's right there's a debate of that, but I think most studies that find motion sickness in people without an inner ear, they've not done their work properly, or they have questionable control. So basically, for all intents and purposes, without an inner ear, you don't get motion sick. So the inner ear is always involved. You have, and this is important to understand the problem, you have two systems in the inner ear, one that detects acceleration in rotational terms. Those are the canals filled with a liquid. I may have, no, I don't have an additional. So this is a bony structure like a hula hoop ring filled with a fluid called the endolymph. And when you make a quick head movement, the endolymph lags behind a bit, behind the movement of the bone. And then there's the cupula, which you can't see here, that is a sensor that basically senses how much shift there is between the bone and the fluid, and then transduces acceleration. It habituates very quickly. So if I put you on a rotating chair, within the latest 30 seconds, probably sooner, if I rotate you at a constant angular velocity, you don't feel that you're rotating anymore. And the moment you make a head movement, you get funny sensations of somersaulting, because the canal that's sort of in the plane of rotation then gets moved out of that plane of rotation and senses movement all of a sudden. Then there's the system here in the utriculus and the sacculus, which senses linear acceleration all the time, basically. So imagine a hair cell, just like a flexible hair with a little weight at the end. It's usually a calcified piece. And as you stand upright, let's assume a hair cell that's growing horizontally will get bent downwards because of gravity's pull. If then you duck, it'll be pulled up a bit, and then it'll go down again. If you make a head movement to the side, the hair will get stretched a bit, but nothing much happens. But a hair cell that's growing vertically will get innervated by the inertia of the little weight at the end of the hair cell. So in these organs, we have hair cells growing in all directions to transduce linear acceleration. In the canals, we have hair cells transducing rotational acceleration. So we are in trouble whenever we're moving at constant speed, because it takes acceleration for the system to work properly. So as we swing around, we're fine. The visually experienced change in the retinal image corresponds to the accelerations that we pick up in the inner ear. But if the two don't correspond, we have a sensory conflict. And this conflict is sort of interesting because it's complicated. So we have an ongoing conflict between the two afferent information flows from the eye and from the inner ear. But we also have a conflict between the afferent input from the inner ear and the expected visual outcome. Right? If I sense that I'm turning left, my brain, right from the inner ear, my brain anticipates a visual shift of the retinal image in the opposite direction. And if the anticipated shift doesn't occur, we have a conflict. Or if you wear goggles, or you provide a large screen display with motion to one side, you expect a vestibular signal that you don't get in the case of wearing a head-mounted display. So this is the sensory conflict theory that comes in two varieties. So there's the the brute ongoing concurrent conflict between two afferent signals. And then there is the theory of that mostly hinges on anticipation between expected input, afferent input, and predicted input by the respective other system. Wimbless and Yelter Boss to buy into this theory. Jim Reason into the classical conflict, and they both contribute, I think. Then there is postural instability theory that basically claims that you only get motion sick when you're uncertain about how to stabilize. So that natural postural stability mechanism is somehow upset, then you get sick. It has nothing to do with the conflict. Wow. So this is a theory pushed by Tom Stoffregen in particular, and it's obviously correlated, right? If you're motion sick, you sway more, and if you sway a lot because your inner ear isn't functioning properly, you get more motion sick. So there's something to the correlation, but it's questionable. It's really the cause. And then there's eye movement theories, and there's poison theory, and so on. There's a few others, but the main theory I'll focus on and I believe in is the dual conflict between the afferent information coming in and the incoming information and the prediction. The state of the art is or was before we got into this was basically that people measured motion sickness using the SSQ, the Simulator Sickness Questionnaire, that came out of work with pilots and astronauts in the 60s. And something just fell here. So the Simulator Sickness Questionnaire is a nightmare because it asks for a list of I think 30-some symptoms. Say queasiness to the stomach, 0, not at all, 1, 2, and 3. Do you feel that you're sweating a bit? 0, 1, 2, 3. And then these scores get summed up and multiplied to a nausea score, and another subset of these question scores gets summed up and multiplied to a oculomotor score and so on, and then it all gets mushed together to form an overall score of motion sickness. The problem here is that the single ratings get used multiply, and strictly speaking, the data you get out of this is ordinal data. Right? You can tell somebody with a score of 60 has more motion sickness than somebody with a score of 50, but you don't know. I mean, the scale is certainly not linear, and it's not interval scale. So it's an ordinal scale basically, but people treat it like an interval scale. They do multiply and run ANOVAs on it and so on. So it's questionable. Here's an example of it's in German, isn't it, from Marco. So this is what I just mentioned. So this is how it gets scored, and you have the nausea, the oculomotor, and the disorientation subscales, and a total score. This is how it gets all summed up, and it's a mess. So the dizziness scale goes from 0 to 292. The oculomotor scale goes from 0 to 195. In the total score, if you look at question 5, right? Question 5 enters twice into the total score, but question 7 only enters once into the total score. It's a mess, but that's the most frequently used tool to measure motion sickness. Simulator sickness questionnaire. And what you find, here we have the English translation. So the 3 scales are intercorrelated, So they're overlapping, and they're being treated the way they shouldn't be treated. So it's I think it's not a good tool. Most experiments using the SSQ get fairly low scores. So they compare scores of 10 and 30. If you get a score of whatever 180 or so, you're really sick. You probably can continue the experiment. So what we try to do is to see if we can't get a good scale that's well anchored, that captures the total score basically. So we piloted a scale that goes from 0 to 20, where 0 is I feel fine, and 20 is I need the bag, I'm about to throw up. So we have two clear anchors, and we ask people to judge their state every minute while they were watching a video. Let's see if, yeah. So this is what we used as a stimulus for the experiments to validate the scale. So we had people sit in front of a huge screen, so most of the visual field was occupied here, and we asked them to just drive along. Yeah, pretend you're driving this car. This is video footage from the racetrack at the Nürburgring in Germany. And people were just supposed to watch this, and after a while they get squeezy, and they give us a rating every minute, and before and after, as people usually do, we take the simulator sickness questionnaire by Kennedy and Lane, and then can compare that to our results. Our scale we called the fast motion sickness scale. And the nice advantage of this scale is if it does capture motion sickness, it can be used very quickly at short intervals, so you can get nice progression scores. The SSQ takes too long to administer, so there's usually before, after, what people do, maybe sometimes in between. Let's see, do I have a slide here? No. So basically, what we find is that the correlations between the total nausea score and the FMS are about 0.9, 0.89, 0.9. So they're extremely well correlated. And then if you look at the subscales, they're also well correlated, and the subscale nausea is correlated at 9.3, so it's the best. So we have a very good correlation with the nausea subscale, even though it's questionable whether you should run a correlation study on this anyway. So we measure this pretty much the same stuff, and we measure it much quicker. So once we had established this quick measure, we got down to business and asked a bunch of questions. One idea that was entertained a lot is that, well, these cyber displays, the head-mounted displays, are particularly nauseating and much worse than other stimuli, maybe because of the pressure on the head, because they're heavy or whatever. So we wanted to figure out whether this is actually so, because there hadn't been any studies to do this properly. So we compared a power wall, a large projection screen, and a head-mounted display by equating for visual angle and resolution. So in both cases, we showed one group. So this was a large display screen here. People were sitting with a chin rest, so they couldn't move about, and they were watching the race. Yes, please, yes.
You have a kind of office chair that rotates as well. Is that important or not? Do you share, or you should have a fixed chair or not?
Well, we adjusted for tall people. It's more comfortable if they sit, so they can easily fit their chin.
About the horizontal plane, more like.
Oh, they were, yeah. right? This experiment takes a while, so if they shift their butt a bit, that's fine.
Okay.
As long as, right, we try to, and even, they could move their head a bit, right? We didn't want, some labs do bite board, so individual, right? But this is not, we're not recording eye movements here, so we let them a little play, but we made sure that their chin was in there, so they were pretty much centered on the display at all times. And this is the Envision display it was really heavy. It had wonderful resolution, 1280 by 900 something. But at the time, this is 20 years ago. So it was expensive and heavy. And lo and behold, so these are the peak FMS scores that people gave us, those who survived the experiment. And we had a criterion to abort when they reached a score of 15, which turned out to be quite wonderful. So in the olden days, there were people who actually had to throw up. And with the cutoff at 15, we didn't have a single case where people had to. So we usually caught the nausea before it got too bad. So the power wall is the gray bars, and the HMD is the black bars. So if anything, the power wall was worse. We have the typical gender difference that we find. Women do a little worse. They get nauseous a little quicker than men do. And the HMD was not worse, but rather more benign. And this is when we count the individual symptoms that people mention. So did you feel sick to the stomach? Did you feel dizzy and so on? So we basically,
Sorry.
Yes.
Okay. I lost a bit of information. Was the same video displayed in both?
Yeah, of course.
It was not like a 3D stereo video. The headset.
Well, it was a 2D film.
Okay.
And it was displayed in both eyes. So you had synoptic viewing, same. So stereo was removed. So you could argue that you had a conflict, right? You saw where the screen was, and you got a stereo information about the screen surface, which you didn't really have with the collimating lenses and the head-mounted display. So the reasons why the HMD was more benign, we don't know from this particular study. So here's the nice trace. So these are ratings every minute. People start at 0, and then you can see that with the power wall, right, the curves differ nicely. So early on, the power wall is more nauseating than the HMD. So you get nice development curves here, and you can sort of extrapolate here and see where they get over the top. But these are the people who did not drop out and who got an average of 9 at the end of the exposure. It was like maybe I think it was 18 minutes. This was the head-mounted display as it was manufactured, and the power wall, which had a much larger field of view. Now I think the modern HMDs have like 110 degrees. This one had closer to 50, if that. Let me see if it's coming up. So of course we need to control for field of view and resolution and stereo. This answers your question here. So these are the values here. So the HMD had a field of view of 48 degrees times 36. So we created a mask to have the very same field of view on the power wall, and we tested a large and a small field of view, so we artificially shrank it with the synopter that we put in front of the power wall. So this is a mirror device that you will see in the next slide. So we have mirrors here, see-through mirrors, so that both eyes basically get exactly the same image. And to make sure that it's not the funny thing in front of their eyes, we have a fake synopter, just two holes. This is just a drawing how it works. So basically, both eyes get the view from the right eye in this particular synopter, and this way we could vary the field of view and see if that made a difference. This is the other side of the fake synopter, and this is what we used on the power wall. So just a cardboard cutout to provide the larger field of view. So we basically had a power wall with a large field of view from before. Then we had the head-mounted display with a comparatively large display. We had the synopter with the stereo conflict removed, and then we had the reduced stereo conflict with a small visual field on the power wall. So we ran all these conditions between subjects, and here's what came out. So this is again the FMS judgments. The blue line is what you saw before. That was the entire power wall visible. And then all other conditions, so all the reduced visual field conditions, and no matter whether you used the synopter or the fake synopter, they were all a lot less nauseating. So there's something about the big screen that makes it particularly nauseating. And it's not the field of view when it's controlled, and it's not the device, which came as a surprise to us, because, well, if you think about it, what is different in the first experiment? Well, you see the entire screen, but you also see parts of the lab around it, and that's particularly nauseating. So our conclusion from this is that there must be a contribution to motion sickness that's merely visual. So if you have an intravisual conflict between the lab space that's still and the foveated region that's moving, that seems to be particularly nauseating, which is odd. Again, we have the small gender difference here, and the power wall wins, if you will. So apparently there is an intravisual conflict. Now the question is the experience of vection important there? About 80% of our subjects said that they felt vection, but this didn't really matter whether they were looking at the power wall or the HMD. So what you normally assume that the head-mounted display is more engrossing didn't seem to be the case. The like vection. So, do you know what vection is? So the feeling that you're moving as opposed to something out there moving, right? So you could look at this video and think of it as a car moving around in the world, or you could think of it as you moving through this racetrack. And when you experience self-motion, that's vection. So vection seemed to be crucial, but it was as easily attainable in the head-mounted display as in the big screen. So the next question we asked was whether the type of motion that you present matters. So if the conflict theory is correct, then the more visual motion you introduce in the display, the sicker people should get. And in short, this is so. So what did we do? We tried to have a controlled exposure to motion where we control for the quantity of angular motion, if you will, and change the quality. So we basically used roller coaster, I'll show that in a minute, roller coaster simulations where the entire movement along the track was in pitch only. So this is, as you see here, this is a pitch movement, this is a yaw movement, and this is a roll. So we basically try to equate it in quantitative terms, but in qualitative terms, we either had motion just around one axis, around two axes, or around three axes. So the question was, does the complexity of the motion rather than the quantity, which we know will contribute to it, does that make a difference? So here's a stimulus just going up and down in pitch. Here we have the roll and pitch and yaw, everything in it, and here we just have roll and some yaw. So again, we presented these animations of roller coaster motion, and what we find is basically the data are a little messier than before. This is the SSQ data with the 3 subscales: nausea, disorientation, oculomotor problems, and the total score. We see that pitch is definitely less nauseating than the pitch and roll, or the pitch and roll and yaw. But the two, between 2 and 3 dimensions, there's not much of a difference, maybe with disorientation a little bit. So if you take the SSQ values, if you look at the FMS scores, we get a nicer segregation here. So this is also showing that FMS is a more sensitive measure. So this is pitch only, this is pitch and yaw, and this is pitch and roll and yaw. So it looks like that the more complex qualitatively the motion is, the more motion sickness people get. But again, I think the difference was not quite significant there between 2 and 3 dimensions, but it seems to prove the point that complexity is important here. The next thing we wanted to know is how important stereo vision is. So does it matter, do you get more motion sick when you provide stereo or less for that matter? And so what we came up with is we actually synchronized 2 cameras and recorded live movies from a real roller coaster. So we were, right, for the simulations here, we weren't sure if the stereo simulation would make much sense. So we went for the real thing. And let me see if I can, oops, why did it just change? Okay, there we go. So this is video footage of a roller coaster amusement park in Germany that we recorded by attaching 2 cameras to the front bar, of the roller coaster. And this, of course, is only one camera that you see here, but we recorded it in 3D, and we're able to present the videos in 3D. The nice feature of this particular roller coaster is that some aficionados had put this all into a virtual roller coaster simulator. So the entire course of this track is perfectly simulated. So we could use that simulation and create 4 conditions. So in one condition, we had a computer animated roller coaster in 2D. synoptic viewing. In one case, we had the animated in 3D, and then we had the true footage in 2D and in 3D. So we were, or should be able to answer the question whether there is a difference between the live camera and the simulation. Maybe people get sicker when you have the vibrations in a live camera and so on, and whether stereo makes a difference. And here are the results. So this again was quite surprising. I would have thought that stereo probably doesn't matter much, and that the vibrations you get, or the low frequency vibrations in the real camera footage should make people somewhat sicker. But what happens is only when the two come together. So when you have the live jitter from the camera and you have the real life stereo footage, then people get particularly motion sick. In all other cases, they're about the same. So the combination of stereo and jitter seems to be particularly nauseating, but stereo by itself doesn't carry the day, and jitter by itself also doesn't carry the day. So that was the FMS scores there. And we always find parallels between the SSQ and the FMS scale. So that SSQ, even though it's not parameterized properly, is quite robust. Okay, you have to either ask questions while I speak. So now I have lots of more experiments.
You might want to be selective in what you
Okay,
want to show.
good. Okay, so we varied lightness and contrast. I can probably skip this because we did a experiment on a flight simulator and looked at night and day and high and low contrast. I'll just skip through this. It doesn't make a difference. So that was another surprise. You would think that, given what we know about the perceptual system, that maybe a high contrast stimulus would be particularly nauseating because the motion detectors are at full throttle, and so it doesn't make a difference. You get motion sick even in very low vision environments. The next question is, this is what we did at a very nice cave simulator in Tübingen at the Max Planck Institute. We wanted to see what role vection has in this, and we used a vection nulling technique. So we had central movement going one direction and peripheral movement going the other direction. So we could have a moving stimulus, a nauseating stimulus, but cancel out vection so people did not get the feeling that they were moving. And people get motion sick nonetheless. So the claim that some researchers made that you need to feel self-motion to get motion sick is falsified. You don't need to feel self-motion to get motion sick, unfortunately. Otherwise, you could probably use that. Okay, so in terms of theory, right, the conflict theory seems to carry the day. Postural instability is not. We did in this experiment in Tübingen, we did record eye movements and posture, put people on a forced plate, and they didn't sway more when they were motion sick. So from our experiments, pretty much everything seems to indicate that conflict theory is correct. Which particular kind of conflict is open to discussion, right? So we have the two types of conflicts integrated in this scheme. So let me walk you through this. We have vision, we have proprioception in the joints and the muscles and so on, and we have the vestibular signals. Those are the incoming afferents that get compared. And then we have an internal model that predicts, right, if based on the visual signal, predicts what the proprioception and the vestibular reference should be, and vice versa. That also go in here and create a mismatch signal. So in terms of conflict theory, if you disturb one of these channels, then motion sickness should go down, because all these pieces of information get weighted. And we know that from research on sensory integration. So basically, when you integrate information from several senses, the information that is deviant, right? Let's say one, right? You hear that you're going this way, you see that you're going this way, but your inner ear tells you you're going the other way. Then if 2 votes against 1, the inner ear information gets downweighted. The same when you create noise. So there's actually a gizmo that gets marketed, which is a little buzzer that you attach to your mastoid behind the ear that just creates vibration, and that supposedly makes you less vulnerable to motion sickness. Well, this could work because you're shaking up, making the vestibular signal less reliable, and that's why you minimize the conflict by doing so. You could, in theory, do the same with the visual or the proprioceptive signals. And one study we did here is we had people chew gum while they were exposed to stimulation. So well, since there is a study showing that pleasant odors minimize motion sickness, it could be that positive emotions will sort of calm you down and reduce it. So the chewing gum could work via the flavor, or it could work via the mechanical stimulation, because it's, the chewing action may actually downweight the vestibular signals. And what it turns out that the flavor of the chewing gum doesn't make a difference, but the chewing action does the job. So we think it's chewing gum does a mechanical stimulation. But we also know that pleasant music helps if people choose their own music, not if you prescribe it. If they get to choose, then they get less nauseous with that. And of course, drugs work. The problem with drugs is that they make you drowsy. There isn't a single drug on the market that removes motion sickness and keeps you in a working mode. Right? So yes, it does clear the symptoms, but it makes you so drowsy you're not allowed to do anything on the space station. And that's why we need to rather. Okay, I will leave it here, I think, so we have some time for discussion, and I can put in more details about the experiments. We've done papers on all of these basically. So thank you for your attention, and please ask away.
I have a question. I can start with one question.
Mm-hmm.
So the expectation, it seems to me like there is very good reason, good evidence to think that expectations matter, because of the huge difference between being the driver in a car or being the passenger. I mean, in personal experience, the difference is from being absolutely fine to throwing up. It's just completely worlds apart. So that must be something where knowing that you are the one who's turning and therefore knows what to expect is a factor.
Yes, I agree. I have the same intuition, but I don't know a single study that that properly divvies up the expectation and the control. Right? I mean, if you know you're in control, then that may just soothe you. Right? I could stop the car if I wanted to. I have control if I wanted to, and so on. It may be this feeling of control that does it, rather than the anticipation of the next turn. But we do know that I've been doing this for 20 years now, right? And or longer. And car manufacturers have never been interested in this. And now all of a sudden they're really interested in it because they realize in autonomous driving, right? In particular, if you have a sealed interior, people watch a movie or they sit against the direction of motion and they play chess or whatever, they get sick. It could be because they can't anticipate where the car is going. It could be that you have a maximally possible conflict between vision and vestibular, because normally what you do is when you read a book and you start to get a little dizzy, you look out the window and you have a way to nix the conflict. If you're fully encased, you don't. You have no clue what your actual movement is, no visual clue. And of course, the vestibular cues are unreliable. Move at a constant rate. You can't distinguish stopped state from a constant motion state.
Self-driving car is a torture machine, I think.
Yeah. So I think you're right. I think anticipation is a big part of it, but the control, and then we need a nice experiment to separate control from anticipability, whatever.
So, what about experience?
Okay.
Yeah. Person gets experience with it.
Oh, yeah, absolutely. So there's two processes that luckily work. One is habituation. So you have a short-term getting used to it, right? If you avoid, so with the FMS scale, if you avoid ratings above, say, 5 or 6, right, you always tone down the stimulus to stay at acceptable levels of slight nausea. Even within, you drive for 10 minutes, you take a little break, you drive for another 10 minutes, you take a break. The motion sickness scores go down. But if you exceed a limit that may be personally different, then you get a runaway process. So then you can't really go back to zero. And then, so there is habituation with submaximal exposure, and there is adaptation. So you can take a rest of a week, go back into the same experiment, and your motion sickness values will be lower. So there's short-term habituation to the stimulus, and there's long-term adaptation. The problem with this is that the adaptation, ideally, you would just adapt people, and then we're done with it. The problem is that the adaptation is extremely stimulus specific. So if you adapt people to a hilly straight shot road like this, you adapt them to pitch movements of the head, and then you put them in a terrain where you make turns like this, the adaptation goes to hell. So the adaptation is very specific to a particular movement. And it's difficult, if not impossible, to achieve generalized adaptation. But that would be one venue. And we're actually currently working on vestibular training to create general adaptation. Yeah. So,
from the graph you showed before, it seems that everyone was experiencing a certain level of sickness. So,
well, these are averages. So some people stay, well, there's always, if you test 20 people, there's a few who stay very low, 1, 2, maybe 3. And there's others who go up to 15, so they have to abort the experiment. And depending on the dose, right, you don't want to lose too many subjects to have reportable data. And you don't want to have the stimulus too mild, so you don't. So it's yeah, but there's a lot of individual variants.
It's like a continuum from people who are low and people who are high in sickness,
Yeah.
or it's more like a subgroup, like people who are experiencing like a sort of disease.
It's pretty much normally distributed, except for people in the very high range. So people who get very easily motion sick. I think there's so much anxiety around it that they seem to just blow out. So I would say it's right. You have a Gaussian distribution, but at the high end you have another peak. So it's almost bimodal. But then again, there's only 10% or less that get severely motion sick. But those are, of course, the people we should focus our countermeasures on, right? We want everybody to be able to be driven autonomously. So, but it's so I think in terms of the sober conflict without additional anxiety it would be normally distributed. And then there's some people who never sign up for our experiments because they're so late.
Just another question. So in the case, for example, the car, it doesn't change anything. For example, if you put the person in a certain situation and the name is big much, maybe less. I think that.
No, we in the one study we controlled for that, so we would be sure it's the quality of emotion rather than the quantity. Yes, but if you show longer exposures, if you show faster speeds, it usually contributes. It makes things worse. Yes.
Another question, which is a little bit related to the problem of expectation and control. Do you know if it is possible to kind of exert a top-down control on integration, in the sense that if I'm able to anticipate what's coming next, this might reduce the subsequent conflict. In my experience, when I go on roller coaster, if I anticipate that the motion that comes next, it reduces my sickness. So do you know if there is any evidence of the fact that the top-down control can also reduce physiologically this kind of conflict?
Yeah, what is top-down control? I mean, anticipation is that top-down? And yes, I think anticipation does help. We're actually about to do a study on a helicopter simulator where the trainers complain about motion sickness, and we want to find out whether it's actually because they're I mean, they tell the student what to do, right? So here's the student flying the helicopter. The trainer is standing next to the student, and he's giving the shots. Okay, fly over there and try a landing maneuver or something like that. So in terms of top down, the trainer calls the shot and tells where the student has to fly. But in terms of anticipating exactly what will be done next, the student is closer, but the teachers get sick, and it could be because you need the fine-grained anticipation that's helping, or it could be their funny vantage point. So the simulation is made for the person in the driver's seat, and if you're in the wrong station point, you may have more of a conflict between visual and vestibular. So we want to figure that out. So this is on a motion platform.
And I think that I was thinking that one specific feature of the programming, the simulation, the characteristic of that track is that you don't really know where the track is going. So maybe that we can compare the degree of motion sickness for tracks in which the curves are unpredictable.
Yeah.
You can see them a little bit in advance, and the low occurring, which is very challenging even for expert drivers because you don't really see where the track is.
Mhm. Yeah, you don't. Yeah, you have to know it by heart.
Yeah, you have to know.
The problem is, how do you provide that knowledge without adapting them to the stimulus? Right, you can't provide the knowledge about the track by having them drive through it, because then you get into adaptation processes. So to tease them apart, you would have to give them a map and see if they can. Yeah, it's difficult to do the experiment. Yes.
Bye-bye.
This question. So, what about different modalities for anticipating the direction of motion? For example, I'm thinking giving some information about the direction of motion on the straight with, for example, auditory stimuli or haptic modalities like vibration just before a turn that is not immediately visible.
Mm-hmm. Yeah, no, that's a very, very good point. I have one doctoral student in the Volkswagen research unit, and that's what we will look at. Does a cue, a tactile cue or an auditory cue, help to anticipate, and will that reduce motion sickness? Yeah, so that's like, and that will probably also get at the question, well, does anticipation per se help? Because there you have an immediate, right, you can always give the tactile stimulus just before a turn, and it should do the trick. It should help. There's a few studies on visual anticipation cues, but they've been done such that people could always look outside a bit. So there's the study I have in mind is that, yeah, people were driven around autonomously, but they were not cased in, so they could peripherally see the outside world, and they had to read a story on a tablet, and then before I think this was deceleration and acceleration case, and before deceleration, some arrows would flash in this direction, and others would, before a braking maneuver, they would flash into this direction. And that didn't really do much, but I think it's because they were also getting some visual cues. So it should help. It should. I'm convinced if the experiment is done right, the being able to immediately anticipate accelerations and turns should help. But the study needs to be done.
Okay, just one last. As anyone tried to use the vestibular caloric stimulation or electrical stimulation to try to reduce the motion sickness?
With caloric stimulation, you increase it. I mean, it's very upsetting.
Even if the caloric, because if I remember correctly, depending on the way in which depending on the temperature of the stimulation, and if the left or the right receive the hot or the cold, you can like induce the perception of moving of action in one direction or the other direction. So probably it can be matched to be in synchro with the video.
I don't think people have tried with galvanic because to get the temperature to shift the endolymph beta is quite a massive interference, and it's a typical tool for ear doctors, right, to see if the thing is working, if the system is working. There are studies on galvanic stimulation, so you can by attaching electrodes here behind your ear, you can, and depending on whether where you put the reference electrodes, you can actually stimulate the vestibular nerve such that people get, well, I don't know how precise it is, but you can induce a tilt forward or a turn roughly. And with so with galvanic stimulation, this has been done, and there are people who claim that they can introduce specific illusory movements this way. The motion sickness studies I know that have used galvanic stimulation, they were all in the sense of noise. I don't know a single study that has used qualitative galvanic stimulation, but in theory it could be done. I mean, certainly if you stick the electrodes into the nerve, in theory it could be done. But then what will you do to prevent motion sickness? You would have to create appropriate vestibular stimulation that's consistent with the visual stimulus, but then it won't be consistent with the proprioceptive cues, right?
But
If
for
you're
example, to test implicitly because before we were talking about expectation, then this way it can be manipulated the time at which the electrical, vestibular and the visual stimulus are right. So if the electrical precedes, it's at the same time or is after the visual, we might find a way to see if some sort of predictive information helps in reducing for example. Another way would be to use
not sure. I mean, to predict the stimulus, you can't use the same, right? If you want to predict a vestibular output, you can't use a vestibular stimulation.
Yeah, because we were talking about experience and expectation, and we said yes, if I study the map, then I have a top-down expectation. But there might be some predictive information which is not top-down. For example, in this case, we can activate the vestibular system coherently with the visual information in advance. Or I don't know. It was just.
I don't think that will work because
That sounds complicated. We'll think about it.
What do you use? I think the predictive stimulus would have to be in a different modality, right? Or no, not necessarily. Well, it cannot be. It should not overlap or interfere with the actual stimulation that you get when you take the turn. So, right? I could show you an arrow to make you anticipate the left turn. So it could be a visual stimulus enabling you to predict the visual scene change to follow. So within vision that works. Within vestibular, if I give you a stimulus that makes you feel a somersault forward to anticipate a movement in that direction to follow, because of the latencies of the vestibular system, I think this will not work because you need anticipation and stimuli a lot earlier, and they interfere with these. And in the visual domain, you can separate, and probably in the tactile, you could have something here or there, or in auditory, you could have different sound levels or pitches for different. But to use the vestibular modality as an anticipation cue, I don't think will work.
I think we need to wrap up. So thanks everybody, and thanks everyone.
Thank you. And have we lost everybody at home? I can't tell.
You can say bye, Luke, as well.
Yeah, there's Luca, there's Maria Pia, and there is somebody else in Italy. Okay, well,
Yes, I'm here.
take care. Oh, you don't see me. I'm waving at you goodbye, but you don't see me. Let me stop. Right now I have no clue what the place is. All right. Bye-bye.
Bye bye. Thank you.
So,